All right, in this second part, they look at a very specific PDE. So they have u sub t equal alpha squared u sub xx. So notice this is a homogeneous problem. And again, I'm just sticking with 0, 1. Okay, so we have that. But now for their boundary conditions, they use a non-homogeneous boundary condition where they keep the, whoops, no, that's a 1. G1 of t, like this, and then the other end at 1, they have the bath, so this would be 1t plus h u of 1 and t is equal to some other time-dependent function. Now, so before, in the last video and in the text, they used alpha and beta. But if I just take, beta 2 or alpha 2 and let that equal h, then that's what I have right there. Let's see. So, okay, so this model again, this would be a model of, at this end, we fix this to be G1 of t, and at this end we have our bath that is G2 of t. It has that temperature, so we actually fix the temperature at the 0 end, and at the 1 end we just put it in a bath, and everything there is insulated along the length of the wire. Okay, and then we have our initial condition that u of x and 0 is equal to phi of x. Okay, so in this case, what they do is they say, well, you go about it the same basic way. The difference is they use, they say, okay, let's let u of x and t, again, I'm going to get rid of the L, so I'm going to have some a of t times 1 minus x plus b of t, whoops, b of t, all right, times x, and then plus uppercase u of x and t. So this is how they suggest redoing the problem. And, notice this is just, if I multiply through, this is just a of t, and then plus x times b of t minus a of t. Okay, so this is a lot like K1. That's a lot like K2. Right, that's what's happening there. Okay, and they say, okay, so we're going to name this function s of x and t. So s of x and t is this a of t 1 minus x plus b of t x. Okay, and we need to choose a of t and b of t to make this work. So we have s of 0 in t. Well, that would be a of uh, um, well, I guess they're just pointing out that needs to be g of 1 of t, I guess, in their work, and then s sub x of 1 in t plus h, plus h s of 1 in t needs to be g2 of t. And so you see, if we do that, then what we would have is that, again, u of x and t is equal to this s of x and t plus our uppercase u of x and t. But if we subtract and we let big U of x and t equal little u minus s, then we see that u of 0 and t equals 0, and then u sub x of 1 and t plus h u of 1 and t would also equal 0 in this case. Okay, so so if we insist that our function here satisfy these two end conditions, then we'll have the situation we want. Oops, I got sloppy here, so sorry about that. Those are uppercase U's. Okay, so we would have those homogeneous boundary conditions for those. All right. And so, you know, if we just plug things in, then s of, whoops, got bigger, s of 0 and t, so if x equals 0, we just get a of t. So we would have that a of t, in this case, is just our function g1 of t. However, b of t, okay, so the other end, so we have to come here, right? We have s sub x. So if I want to take the derivative of s with respect to x, I'll get I'll get a negative a of t plus a b of t. Okay, so we get s sub x is well, of 1 and t is that would be a minus, right? Back here we got a minus, so we would have a minus a of t plus b of t. Okay, so we have that, and then h times s of 1 and t, and if x equals 1, right, then that disappears and we just get the b, and so this is h times b of t times x, and oops, not times x, because x is 1, sorry, so just b of t, And so what we have here is that minus A of t plus B of t plus H B of t. Guess I don't need that parenthesis there. Is equal to G2 of t. And A of t again was G1 of t, so we get B of t. Factor out the B of t, I get 1 plus H here. And we have is equal to, this was G1 of, minus G1 of t, so I get a G1 of t plus G2 of t. Now divide by 1 plus H, and we get our B of t is G1 of t plus G2 of t over 1 plus H. And so our S of x and t is G1 of t times 1 minus x, and then plus G1 of t plus G2 of t over 1 plus H, all times x. Well, this is fine. So what we see here is if I take S sub xx, I do get 0. Okay, so in this case, it is true that U sub xx is equal to uppercase U sub xx. So that's all fine. But unfortunately, not the case with S sub t. S sub t is equal to G1 prime of t times 1 minus x, and then plus G1 prime of t plus G2 prime of t all over 1 plus h, all times x. And so when we look at U sub t, that is definitely not equal to little u sub t, because we've added that stuff in. And so unfortunately what happens then in the original problem where we had, even if we had a homogeneous problem, u sub t equal, say, alpha squared u sub xx, if we had that, well, now our new problem is uppercase u sub t equal alpha squared u sub xx. But see, now we end up here with our I gotta think about whether this is a plus or a minus. I guess this is a plus. And so plus S sub t S sub t of x and t. Okay, so the problem is now this is non-homogeneous. We don't know how to solve this problem. Okay, we can't do it with separation of variables. So we would be, we would be stuck here as far as trying to solve this problem. So we can transform the boundary conditions, but unfortunately, we don't know how to solve the problem. So we can change it to, something where we do expect a particular steady state, you know, that's our s of x and t, but unfortunately, yeah, I can't just say, oh yeah, well, this is going to be, you know, we're going to get the coefficients like we did before, and all of that. So in this case, you know, we can get this new function, new initial condition. So, you know, in this case, oh, and I did get that wrong. Sorry, that should be a minus. That's a minus. And so, you know, we have to solve this problem. U sub t equal alpha squared, whoops, uppercase U sub xx minus s sub t of x and t. So we can write down what that is, but yeah, it doesn't help a whole lot as far as our solution. And then we have our boundary conditions, u sub x. Well, they've written them backward. I just noticed. There are little things that, yeah, are kind of strange here and there. So I would write this as u of 0, t equals 0, and then u of, and I'll use a 1 again, u sub x of 1 and t plus h u of 1 and t is equal to 0. And then we'll have our initial condition that u of x and 0 is our old phi of x, but then minus s of x and 0. Okay, so you know, we know what this function is. We know what that is. We can do all that, but the problem is we don't have a technique for solving it. Okay, so that takes care of their more complex boundary condition. So we'll stop there.